All right, so this animation here is good for pressure, volume, temperature relationships of gas. So if we take this pump and pump some gas into this container, okay? So now we put some gas in here, and if we heat it, what's going to happen to those particles?
They're gonna collide.
What's going to happen to the pressure?
It's gonna go up.
Let's find out.
There's more collision.
So we're adding some heat. Temperature's going up. 800K, 900, 1000K. Look at the pressure. Pressure's going from 1.7 to ATM. So the concept here is the particles are exerting a lot of pressure till it does what?
Explodes. I got a question though.
Now,
why is there a brown astronaut?
our spaceman, hold on, we'll get to that. All right, you want to put the heavy species in this time? Let's do that. Okay. All right. So now the heavy ones move slower, right? Does that make sense?
Yeah.
Okay. Now, what if we cool it down?
They're gonna go slow. They're gonna.
Oh my.
Will they move even slower?
Yeah.
Is that deflation? Just putting ice cubes under a box.
That's what we're doing. It's ice cubes under a box. Okay. So they're moving very slow. Okay, good. Let's heat it up a little more just for fun. All right. So we heat it up. Particles gain what?
Speed.
What kind? Kinetic energy. Gaining kinetic energy, right? Temperature's going up.
What if you keep pumping?
Do you want to add some more gas in there?
Yeah.
Make it full of gas. Yeah.
You can put both species in there if you want. Get crazy.
Turn off the
Oh my god, so cool.
This is
Look at all those what?
chicken.
colliding, collision.
Collisions.
Radical.
Now, what's our spaceman here for?
He's just the fourth.
He's
gonna
compress.
He's going to compress it.
Oh hey. Whoa.
Yo, WTF is that, mate?
So he pushes. So what's shrinking there?
The volume.
So what's increasing? Pressure, right. So it's a cool animation for all these fun things. Back to moonwalk. All right. Done with that. Okay. That was fun.
That was exciting.
All right. Now, this steel drum is being heated, just like that can I did, except this is a larger scale. They heat it up, and then they put it in a little swimming pool type thing.
Why can't we do that?
We can if you guys want to bring in a steel drum.
I can do it. I got old
No.
oil containers.
It'll melt. So now they're trying to cool it down, so it does what?
Implodes.
Just what that can do. When I put the can upside down in the cold water, it crushed, right? It imploded, so here we go. The teacher sprays it with cold water.
There, we're too close.
Correct.
Pretty sweet. Okay.
Yeah, that one. It's in one of those.
Oh.
Yeah, it's the same thing.
Oh my god.
Yeah. So if you don't properly vent it, I can just, I guess, assume it doesn't regulate the temperature or the pressure. So the same concept.
Oh my god.
The outside pressure crushes it because the inside pressure drops.
That was cool.
Oh, there it is.
That's so
Yeah,
cool.
that is pretty cool. All right. So now here's where the notes come in. So we're basically done with, those are just kind of for fun and also understand the concept, more just fun. But so we're done with gases. We spent a lot of time talking about gases, gas laws. The lab we're doing is on gas laws. But inside the syringe, I think we all had a chance to do the lab now. Inside the syringe, what did we put that small amount of liquid? Acetone. Okay. Hey, you two, stop talking. Pay attention. So acetone heats up, and what does it do inside that syringe?
Bubbles.
Boils. Okay. If it boils, it's producing a lot of this.
Vapor.
Vapor, right. So inside that syringe, you have a lot of vapor pressure. Now, put the sequence of events together here and then raise your hand if you know the answer. When gas particles collide, they create gas pressure. When air particles collide, they create air pressure. So what's vapor pressure? Raise your hands, raise your hands. Gas particles collide, that equals gas pressure. Air particles collide, that equals air pressure. So what's vapor pressure? Raise your hands. Caroline. Vapor particles colliding, very good. So the one I had this morning was better to see through it, but in here there's a certain amount of water. If I put the cap on here, inside here, vapor pressure will build up because the water is giving off vapor. And eventually, the vapor in here actually starts going back into the water because it's sealed. There's no way it's getting in or out. So the concept of vapor pressure is what we're talking about next. Liquids and vapor pressure. And here's a question for you guys. Can you boil water without heating it?
Sure.
Probably, yeah.
Maybe.
Have you ever seen it?
Yeah.
No.
Yeah.
Well, I'm going to show you. I can boil water without heating it. Why do we have to heat water to boil though under normal conditions?
Because the room temperature. No.
What is boiling? Usually people don't know this unless you learn in chemistry. Yeah, but it happens very quickly, right? Here's the concept. You have water and the surface of water. Water is evaporating into vapor above it. Well, the air pressure is pushing down. So you have water vapor pressure pushing up and then air pressure pushing down. When those forces are equal, water boils. Which force do you think wins most of the time?
The what?
Air pressure. Otherwise, water boils all the time. So air pressure is always stronger pushing down. When you give the water heat, you're giving it energy to create more vapor pressure. So when you give it heat, it pushes back against the air and it boils. So without heating the water, how would we boil it?
Take a really
Pressure.
hot air.
If you're following what I'm saying, if we give water energy, heat it up, it pushes up against the air. Well, let's say we don't have heat, but we want to boil the water. Take a-
You put it in a vacuum thing.
Right, good. Take away the air pressure. So if you decrease the pressure pushing down, the water will boil. What does water boil at in this room? What temperature? 100 degrees Celsius. On top of Mount Everest, I think it's like around 50 degrees. It boils at 50 degrees. Why?
Air
Air pressure is so low. Right, who was on top of the mountain in the drawing? Trevor?
Yeah.
With the long hair and the
Sombrero.
sombrero, and who was at the bottom?
Nick.
Nick, right.
The machete.
So, right. Nick had the machete, right. I thought that was period 2. So, yeah, at the bottom there, Nick's boiling water at 100 degrees. All right, Trevor's boiling water at 50 degrees on top of the mountain. So, that's all the stuff we're going to talk about. This video explains 2 things, vapor pressure and dynamic equilibrium. I didn't give you a word of the week. That would have been a good one. So, I'm a little bit late on that, I know. So, I'm going to give you one tomorrow. So, 2 words I want you to write down in your notes right now. Vapor pressure and dynamic equilibrium. We're going to title this though, so hold on a second. The title of the section we're talking about now, liquids and vapor pressure. Liquids and vapor pressure. So tomorrow I have a demo that involves fire, so that'll be fun, and it helps you understand vapor pressure. So we're going to define vapor pressure. Now the way he defines it in this video is not super great, so don't write down exactly what he says, just pay attention. Afterwards, we'll write it down. So first we're going to define vapor pressure, then I'll explain the term dynamic equilibrium, but he's going to tell you what that means, okay? So it's only 2 minutes, we'll watch this, then we'll take a little bit of notes, and then if I have time, I'll go over number 11 on the back of that worksheet, and then that'll be it for today. Yeah, you don't have any homework. Here we go.
After you've kind of seen the results of what happens when you start studying intermolecular forces, and we start making a little bit more of a condensed phase, such as solids and liquids, you start getting all these unique properties of solids and liquids. Liquids have quite a few unique ones: viscosity, surface tension, and one of the more unique ones is vapor pressure. That's a very special case, and that's probably another thing completely. So let's just think about it. If you take water in a container and you allow it to start evaporating, the space above the surface of the water will start getting water molecules. That means it's a gas now, and gases impart pressures. So as that builds up, what's going to happen is these particles floating above the water can go back into the water unless they're whisked away.
So if this container is open, will the water go back into it? No, the vapor will go into the atmosphere, into the room, right? So the next thing is they're going to put a top on.
So, you put a lid on the container, all the particles are trapped, so the water starts going back into the water phase, right?
Okay, so we got water coming out. What's that called? Right, what's that process called? Evaporation. And if it goes back into the liquid,
Condensation.
condensation. Good. You guys ever been to a hotel or any kind of office building or building in general with the rotating door?
I'm in a building right now.
Rotating door. Stay with me. Stop, you know, the wisecracks. So the rotating door. We've all been in one of those?
Yes.
Okay. Hope so. Imagine you had a line of people outside the building, a line of people inside the building. So the surface of the water would be where the rotating door is, revolving door. So people, let's say, outside the building are leaving. People inside the building, or outside the building, are coming in. So people are going in and out literally at the same time. So we could use this door as an example. It doesn't have to be a revolving door. I'm trying to give you a visual. Let's say we had 10 people in the hallway and we have 20 people in here. Olivia walked out, but one person from the hallway came in. Would there be any change in the number of people in here? Would there be any change in the number of people out there? No. So that is called dynamic equilibrium. He's going to explain that, but I like to explain it first so when you see it, it makes more sense. It's when particles start changing at the same time. The word dynamic means change or movement. Equilibrium, what do you think that means?
Equal.
A lot of students want to say equal. It doesn't mean equal. How do we spell equal? E-Q-U-A-L.
Yeah.
Equilibrium is E-Q-U-I-L. It's two different words. So, equilibrium does not mean equal, it means something else. We'll get to that in a
The water
second.
vapor goes
So
back
watch.
in. As this happens, you finally reach a state at which the exiting evaporation rate equals the entering condensation rate.
What's the word rate mean?
How fast?
Oh yeah, fast, right? So evaporating is occurring at one speed, and condensing is occurring at the exact same speed at the exact same time. That's what he's talking about.
You reach what we call equilibrium. So when those two rates equal, you establish a constant pressure inside your container. That pressure is called the vapor pressure of that liquid.
So he's not wrong. This guy's he's a chemistry professor, so he's not wrong. The way he explained it is 100% right. But what I need you to write in our notes, which we're going to do right now, is a little simpler definition. So vapor pressure is what did we say it was? Vapor pressure is
Pressure.
vapor particles doing this.
Colliding.
Colliding. Vapor particles colliding with each other and the container. Now, where does vapor come from?
Evaporation.
It came from somewhere though. A liquid or solid. So remember, gas pressure is from gas particles. Vapor comes from liquids or solids. So that's the difference there. Vapor comes from liquids and solids. So vapor particles colliding with each other in the container. In a sealed container, the vapor pressure can build. It can increase to a certain point. That's what he's talking about in this picture. So inside my water bottle, if I put the top on, the pressure will build to a certain point, then it stops. It's not going to just blow up. If I put the top on here, it's not going to build pressure and then pop the top off. We'd have to heat it, right? So it's going to increase if it's sealed to a certain point. If it's open, it's just going to go in the atmosphere. Okay? So, well, I'll leave that for a second. We'll let him finish here.
Okay, so water, you would say it's the vapor pressure of water. It's an example of what we call dynamic equilibrium, meaning when you look at the thing, you can't tell anything's happening, but in actuality, there are billions and billions of molecules leaving the surface of the water, and there's also billions and billions re-entering, and they are exactly the same rate. So there's no net change, but you have established what we call a vapor pressure.
That's what equilibrium means. No net change. Give me one word that explains no net change. Constant. Very good. Equilibrium means constant. So we're going to write this down. So basically what this concept is if you look at this picture, the level of water would never change. Because every time one particle leaves, the other one enters. That's the analogy of the revolving door. Or walking out of the room. As long as someone comes in, takes your spot, nothing really changes. Not as far as numbers. So, dynamic equilibrium draw a beaker, pretty big, with some sort of lid on it. Let's actually, Autumn, when you get a chance, hit the lights, please. We're going to have one arrow going up, kind of like they have there, one arrow going down. So this arrow here is evaporation. This arrow here is condensation. What? It's not from out there? It's out there? Really?
Yeah.
Sound like it was out
It's not a bird.
Alright.
Who's gonna be out there?
So evaporation going up, condensation going down at the same rate. So the evaporation and condensation at the same rate. So what that means, I'll have to write it here, I'm out of room there. What that means is that the amount of water, of liquid and vapor stay constant. They stay constant. Underline that word constant. Sorry. The word equilibrium, yes, sounds like equal, but has nothing to do with equal. It has to do with being constant, like Katie said. So, again, one particle goes up, another particle comes down, so it never really changes. And that's what he explained. That's really important to remember down the road, especially when we get to a unit called equilibrium. So, those are the two things we're going to be talking about a little bit more tomorrow. And hopefully I'll have time to show that demo tomorrow. So, get that down. We'll review that again tomorrow. Real quick, I'm going to go through 11. We got a few minutes. I'm going to try and get this done. So, go back to the homework. Look at your setup for number 11 and follow me on the board here. Here we go. Okay, number 11, we got 22.4 liters. That's my V1. At 20 degrees, we convert that to Kelvin, 293. 750 torr is our P1. So that's our P1, V1, and T1 for 11. Let's see, what volume, so X goes for V2. Will occupy, let's see, standard temp, 273, and standard pressure, 760. So for number 11, check your work. It should match that. Cross multiply these three, cross multiply those two, divide, bless you. And again, the answer was 20.6. I just wanted to show the setup in case you were confused about that. I gave you standard pressure, and the standard temp was on table A. So that's where you would have got that from. All right, so we're going to stop. The bell's going to ring real soon. No homework. I am after school today and tomorrow if you need help. All right. Does anybody owe me anything? Oh, the test.